as we proceed. So
what time is it? It's 6 in the evening there?
It's 3 past 6. So it'll be 8:33 your time.
Yeah.
Right. So, all right. So a very good morning, good afternoon, good evening, once again, depending on whatever part of the world we're logging in from today. And welcome to the 12th talk in the Mysteries of the Universe Institute Lecture Series, hosted by the Indian Institute of Technology, Roorkee. And we are delighted to have Professor Krishna Rajagopal as our distinguished speaker for today. Of course, those of us who work in heavy ion collisions, QGP and the likes, are very, very familiar with Professor Rajagopal. But for completeness, let me try to give a short intro. So he is the William A.M. Burton Professor of Physics, the Margaret McVicar Faculty Fellow and Dean for Digital Learning at MIT. He's globally renowned for his work in QCD at high temperatures and density, whereas the quarks and gluons do not coalesce into hadrons. His work requires linking particle and nuclear physics, cosmology, astrophysics, condensed matter physics, and string theory. He's also known for his work on the properties of the superfluid color superconducting quark matter that may lie at the centers of neutron stars, providing a clear understanding of the properties of matter at extraordinarily high density. His awards and honors include the Outstanding UROP Faculty Mentor Award at MIT, the UROP being the Undergraduate Research Opportunities Program. He's the recipient of the 2011 Everett Moore Baker Award for Excellence in Undergraduate Teaching at MIT. He was elected the Margaret McVicar Faculty Fellow in 2010, the Fellow of the American Physical Society in 2004, and he was a recipient of the Buchner Prize for Excellence in Teaching at MIT in '99. So with that, I would humbly request Professor Rajagopal to please deliver his lecture. Professor Rajagopal.
Well, thank you so much, Professor Mishra, for that very kind introduction, and thank you also for the invitation. It's a real pleasure and honor to speak with all of you this evening in India, this morning here in Boston. So the title of my lecture is Doping and Probing the Original Liquid. And I'm going to start with a fairly lengthy introduction as to what I mean by the original liquid, what that is, and then we'll talk about doping and probing it in a few minutes. Oops, what's going on here? There we go. So the original liquid, I think we're calling it the original liquid is a good name. Unfortunately, in textbooks, it has a different name. It's called quark-gluon plasma. Quark-gluon plasma, and I'll explain why why we now know it's a liquid and why this was not foreseen. So the original conception of how to think about quark-gluon plasma is it's the phase of quarks that you get if you take the temperature to infinity, so to very, very high temperature. In any material system, if you take the temperature arbitrarily high, entropy wins, any symmetry breaking melts away. And furthermore, in QCD, QCD is an asymptotically free gauge theory. That means its interactions are weak when you go to high temperatures. And so we know from first principles that in this temperature to infinity limit, we will have a gas of weakly interacting quarks and gluons. And that was the original conception of the quark-gluon plasma. Now, for about 20 years, we've had first principles calculations in QCD done on the lattice of the static thermodynamic properties of this material. And they show that there is a crossover at a range of temperatures somewhere around 2 trillion degrees, which corresponds to 20 microseconds after the Big Bang. And in more reasonable units, temperature of 150 MeV. At this temperature, this primordial liquid, I'm skipping ahead and calling it a liquid, this quark-gluon plasma, which filled the universe for its first few microseconds, breaks apart into the familiar protons, neutrons, and other hadrons. And the order that characterizes the vacuum of QCD develops. Experiments, which I'll describe briefly, are now producing droplets of this stuff at temperatures 2 or even 3 times Tc. So these experiments are reproducing the stuff that filled the few microseconds old universe. And based on this slide, you would expect that stuff to be a weakly coupled gas of quarks and gluons. One representative result from those lattice calculations, this calculation is more than 10 years old now. And this shows the energy density rising rather dramatically, but continuously in units of the energy density of a non-interacting very weakly coupled gas of quarks and gluons. That's what 1 means here. And you see that at low temperatures below this 150 MeV scale, you have a much lower energy density characteristic of a system of protons and pions. And look at this. The energy density rises to about 80% that of a weakly coupled gas of quarks and gluons. So does the entropy density. And the mistake that we all made before the experiments came online starting in the early 2000s from earlier versions of this lattice calculation, the mistake was to say, oh, look at that, 80% of this value here, which is defined as 1 on this graph, it's within 0.8 of a non-interacting gas. So this must be a weakly interacting gas. We discovered that that was a mistake from experiment, the combination of experimental data and hydrodynamic calculations, which is the story I'm about to tell. But we could have realized this from a completely different direction. It turns out, and this was also clear by the end of the 90s, but people like me weren't yet paying attention. There is a large class of gauge theories that are cousins of QCD. They're not the same as QCD, but they are gauge theories with strong interactions. And these other gauge theories have dual descriptions that allow you to do rigorous calculations at strong coupling. Unlike in QCD, where we have for decades used as a crutch our ability to do perturbative calculations at weak coupling. In these other gauge theories, methods that I'll say a little more about later that are sort of like a gift, calculational gift from the string theory community, allow us to do calculations at strong coupling. And if we'd been paying attention, we would have noticed that in all these other gauge theories, if 1 is the value of the energy density at 0 coupling, at infinitely strong coupling, they have energy densities that are 0.75, 3/4. And so if we'd been paying attention, we could have observed that actually 80% is closer to 75% than it is to 100%. So maybe already from this, if we'd been paying attention, we might have realized that actually this is not a gas at all. It's some sort of very strongly coupled, very strongly correlated fluid. The way we actually learned that was by starting to do experiments at the relativistic heavy ion collider. This is one of the earliest collisions at RICS in the year 2000. 2 heavy nuclei, 1 went into the slide, 1 came out of the slide. They collided right here at the center of the slide and produced a little explosion of stuff, which is what we want to study. And that stuff then expanded rapidly, cooled, sort of recapitulated the history of the microseconds old universe, but much more quickly and at a very small volume, fell apart into a spray of protons and pions, which you see as the colored tracks in this artistic, this image made to look beautiful. 10 years later, at more than 10 times higher collision energies, the Large Hadron Collider started doing similar experiments with 3 major detectors. This picture is the one that looks most similar to the one I showed before from ALICE, also ATLAS and CMS. So at this point, we have lots of experimental data from these 2 major collider facilities, RIC in Brookhaven in the United States and the Large Hadron Collider in Geneva in Europe. And analyses of these data using hydrodynamic calculations, and in particular analyses of how asymmetric blobs of quark gluon plasma expand and explode. Now, why are the blobs asymmetric? Well, if I have 2 disks colliding, 2 pancakes colliding, 2 Lorentz contracted nuclei colliding, they might not collide head on. If the nuclei miss each other, then I'll have, actually, let me do it this way. If the nuclei miss each other, then I'll have 2 circles colliding and the collision will occur in sort of an almond-shaped region. And when an asymmetric blob like that if it's a blob of gas, all the gas particles just fly off in random directions and you get a circularly symmetric collision, circularly symmetric debris. But if the stuff you make is a liquid and it's in an asymmetric shape, then that means the pressure gradients are different. There's more pressure in the short direction, less pressure in the long direction. And so you'll get debris flying off asymmetrically in azimuth. And this is what's seen. I'll show you data in a minute. And this is what tells us that what we actually have is a liquid. And as I'll explain somewhat metaphorically, it has allowed us to determine that this liquid produced in these collisions, which filled the early universe. So this is the liquid this is the original liquid. It filled the universe when it was a few microseconds old. This liquid has the lowest viscosity of any fluid we've ever discovered. Viscosity, the lowest dimensional characterization of its viscosity. And the dimensionless characterization is called eta over S. Eta is the shear viscosity, S is the entropy density. This is a dimensionless measure of how much dissipation occurs when a fluid flows. And the liquid quark gluon plasma, which these lattice calculations were describing without realizing, these lattice calculations were describing its energy density, but nobody was paying attention to its material properties other than its energy density and its entropy density. It turns out this is not a gas at all. It's actually the most strongly coupled fluid that we've ever discovered. And this is what has made quark gluon plasma interesting to a broad scientific community. So you would think I'm about to tell you how to draw that inference from experimental data from these ultra-relativistic collisions of nuclei. I'm instead going to take a detour and tell you about the one fluid we know whose eta over S is almost as small as that of QGP, and it's 20 orders of magnitude colder. It's nanokelvin in temperature instead of trillions of Kelvin. This is an ultra-cold cloud of trapped atoms. These are experiments done by our atomic physics colleagues. And they have magic methods in their atomic physics bag of tricks where they can dial the interaction between the atoms at will, and they can choose to make the interactions between the atoms in their trap very, very strong. And when they do, this is what they see. So this is a photograph of ultra-cold atoms in a trap. And the shape of the trap is cigar-shaped. This is a photograph of a cigar-shaped cloud of atoms. And then you turn the trapping potential off. So you turn the trap off, this thing is going to explode now. If this were a gas, the explosion would occur in all directions because I would just have particles with random motion. They'd fly off in all random directions equally. Instead, what you see, you can just see in the picture in the bottom left, the motion is much more in the equatorial direction of the cigar, much less in the polar direction, which is exactly what hydrodynamics would give you. From comparing these data with literally photographs to hydrodynamic calculations, you infer that eta over S for this fluid is somewhere around between 0.3 and 0.4. So it's the same logic for heavy ion collisions, but here's the data. So this is data from collisions at the LHC. This is 4 different collisions. And if you look at this top left one, that looks pretty circularly symmetric. So maybe that was a head-on collision. This one, you can see that there's much more momentum flow in the directions that I'm showing with my cursor, top right, bottom left, and less momentum flow, top left, bottom right. So this was an asymmetric collision, and the momentum of the debris shows it, and that means it was not a gas. So just from looking at this picture, I can see it's not a gas. This one, the momentum flow is in the top left, bottom right plane, not in the top right, bottom left plane. Here's a funny one. It sort of looks, if you look at it, you one event, you're not sure if this is statistically significant, but it looks like it has almost a flow that is almost in 4 directions. So before we leap to interpreting this data with hydrodynamics, you have to ask the question about how rapidly this system equilibrates, because agreement between experimental data and hydrodynamics can be spoiled either if there's too much dissipation, because what happens with dissipation is if you have this almond-shaped blob, and as it starts to, the hydrodynamics says, oh, almond-shaped blob, it's going to explode with more force this way, less force that way. As that explosion starts, dissipation turns the motion into heat. Heat is random thermal motion, and you lose the asymmetry. So too much dissipation, you lose the asymmetry. But also, another way you can lose the asymmetry is if it takes too long to equilibrate, because by the time it equilibrates and hydrodynamics applies, it's already circularized. So one of the really 20-year-old results from heavy ion collisions is that hydrodynamics seems to work already one Fermi of femtometer, one Fermi of time after the collision. This is the time it takes light to cross one proton. And so this was long seen as very rapid. So for the second time, and I think this is the second of 4 times, we gained some insight from these cousins of QCD. So I'm telling you, I did a collision, and within one Fermi of time, the time it takes light to cross a proton, this stuff I made is well described by hydrodynamics. Is that a surprise? Does that make sense? It was originally seen as a puzzle. How could that possibly be? How can it become a fluid so fast? Well, we now have calculations, not from QCD itself, but in one of these cousins. This is the calculation of a collision, not of nuclei, but of sheets of energy in this cousin of QCD. And what you see here is energy density as a function of time on this axis and space on this axis. So here's a sheet of energy coming in from the left. Here's a sheet of energy coming in from the right. They collide. After the collision, here's the energy density of the quark gluon plasma of this cousin of QCD. And you then can do a hydrodynamic calculation. See, does hydrodynamics describe this expanding cooling fluid here? And the answer is yes, it does, about 3 sheet thicknesses after the collision. And then you realize, oh, wait a minute, what's the sheet thickness at RIC? Well, nuclei get Lorentz contracted until they're about roughly 0.1 Fermi in thickness. So 3 sheet thicknesses at RIC is about 1/3 of a Fermi. In this very strongly coupled cousin of QCD, hydrodynamic fluid forms in 1/3 of a Fermi. So maybe I shouldn't be surprised. Maybe it's okay to use hydrodynamics to describe this situation because of the strongly coupled nature of this fluid. Okay, so I've given you the beginnings of a story that has played out over the past decade, maybe the past 15 years now. Now I'm going to cut to the chase, and this will be, I'm getting towards the end of the introduction of my lecture. So what do you do now? You use relativistic viscous hydrodynamics calculations to describe these little explosions. The little explosion of an asymmetric droplet of quark gluon plasma. But once you start doing that, you realize that, hang on a second, nuclei are made of protons and neutrons, they're lumpy. And so you have to start taking seriously the lumpiness of the heavy ion collisions. And it's that lumpiness which you then is responsible for the fact that in some collisions you see shapes that are not just more in this direction, less in that, but are more complicated shapes. And these more complicated shapes come from the lumpiness of the initial collisions. And you then, if you are paying attention to what our cosmology friends are doing, you realize there's a remarkable analogy between the analysis that we're doing for heavy ion collisions, which you can think of as the little bang. So in a little bang, you collide 2 nuclei, make a droplet of the fluid that filled the universe during microseconds after the Big Bang. So this is, on the left here, this is a representation of the lumpiness of the Big Bang. This is from the microwave background data measured by the WMAP satellite. On the right, this is a representation of the lumpiness of little bangs. Unfortunately, the left is data. Unfortunately, the right is simulation, not data, because you can't take photographs of the little bangs the way you can of the Big Bang. But this is a simulation of the lumpiness of what the initial conditions of heavy ion collision, because they are made of individual protons and neutrons. This lumpiness means that the final state explosion will be asymmetric in all kinds of ways. You Fourier decompose that asymmetry into coefficients V2, V3, V4, V5. These are the coefficients of the different moments of the anisotropy. You calculate those hydrodynamically, those are the solid bands. You measure them in data, those are the black points. And the hydrodynamics describes the data remarkably well at both RHIC and the LHC. RHIC with an 8 over S of 0.12, the LHC with an 8 over S of 0.2 in this calculation. So look at that. I've just extracted the shear viscosity, this dimensionless measure of dissipation, two different collision energies by comparing data to hydrodynamics. And it's completely analogous to what our cosmology friends do when they do a hydrodynamic calculation of the Big Bang. They get the curve shown here, and then they make measurements of the moments of this distribution, which are the black points. And again, hydrodynamics, their hydrodynamics of dark matter and ordinary matter in their case, describes the data remarkably well. So in cosmology, initial state quantum fluctuations, coming in their case from inflation, get processed by hydrodynamics, and then they're represented in the data by these coefficients, which they call C sub L. And from those coefficients, which are measured, you learn both about the initial fluctuations and about the properties of their fluid. So in our case, in heavy ion collisions, initial fluctuations, quantum fluctuations coming from the quantum mechanics of the protons and neutrons in nuclei, get seeded into the fluid, make it lumpy at the first moment of the collision. That lumpiness gets processed by hydrodynamics. It appears in the data as these coefficients, which we call V's, they call C's, but it's the same thing. And from these coefficients, we learn about the initial fluctuations and about the quark-gluon plasma. In particular, it's eta over S. So if you compare these two cases, the cosmologists have one very big advantage, which is that they have measured C sub L's out to 1,000 and in fact now beyond. We've only measured V sub N's up to 6. Here V5 and V6 is now well measured, but we have 6 moments, they have 1,000. But we have a huge advantage. They have only one collision. There's one Big Bang that we get to observe. They have one event. We have billions of events. So we win on statistics. They win on the resolution that they have for our one Big Bang. Okay, so using these analyses, you learn that 8 over S at RHIC is somewhere between 1 and 2 times 1 over 4 pi. 8 over S at the LHC is between 1 and 3 times 1 over 4 pi. So 4 pi 8 over S being between 1 and 2 or 1 and 3, that's a very small value. For gases, 4 pi 8 over S is about 10,000. For ordinary liquids like water, it's between 10 and 100. And for that cold atomic fluid, 4 pi 8 over S was around 0.3, so 4 pi 8 over S is around 3 or 4. But why am I multiplying by 4 pi? It's because, again, for the third time, fourth time will come, for the third time, from these cousins of QCD, in every one of these cousins of QCD, 4 pi 8 over S is 1. So the third thing that we learn from these cousins of QCD is that in a gauge theory, in the limit of very, very strong coupling, when you have an incredibly strongly correlated fluid with the strongest coupling possible, this dimensionless measure of dissipation goes to this value of 1 over 4 pi. And quark-gluon plasma, the original liquid in nature, is within a factor of 2 of that, the value that you get for the strongest possible interactions within the liquid. And so this is then the basis for our understanding now that the original liquid really is a liquid, and in fact, it's the most liquid that we've ever discovered. In fact, it's so liquid that if you try to describe this liquid in terms of particles, you're doomed to fail. There are no quasi-particles in this liquid. And for condensed matter physicists in the audience, this should remind you of strongly correlated many-body systems like the high-temperature superconducting materials, the cuprate superconductors, which have a so-called strange metal phase. And that strange metal phase is famous in condensed matter physics for having no quasi-particle description. It's one of the grand challenges in condensed matter physics. And this fluid that filled the early universe in its first microseconds, and that we now produce and study in these heavy ion collisions, is similar in this respect to the strange metal phase. So that's the end of the introduction of my colloquium. That's the lightning summary of the past 20 years, with a focus on what I see as the most important lessons that we've learned. I want to spend the rest of my colloquium, the main part of my colloquium, on what's next. And I'm going to ask two different kinds of what's next questions. Okay, so we've discovered this new complex form of matter. Newly discovered, of course, it was the original. It's the original complex form of matter, but newly discovered. Anytime you discover a new complex form of matter, one of the questions you ask is, what is its phase diagram? High temperature superconductors, you say, what is its phase diagram as a function of temperature and doping? We're going to ask exactly the same question. What is the phase diagram of this original liquid as a function of temperature and doping? But what do I mean by doping? Doping for us will mean excess of quarks over antiquarks rather than excess of holes over electrons. So that will be our first what's next question. And then, and that's common across, that's a question you ask with any material system. A question that we are privileged to have a chance to answer for our strongly coupled fluid is, how does this strongly coupled liquid emerge from an asymptotically free gauge theory? After all, this gauge theory, QCD, its fundamental fact is that at short distances, the quarks are very weakly interacting. So how do we get a strongly coupled liquid out of it? Those will be the two questions that I want to, that I think will occupy the field for the coming decade and that I want to talk about in the rest of my talk today. So we'll start with the phase diagram. At a cartoon level, this is the phase diagram of the cuprate high temperature superconductors. In a certain range of doping and up to a certain critical temperature, they are superconductors. At higher temperatures, you have a strange metal phase, which I already mentioned. This is the analog of quark gluon plasma for this system. And then over here on the left, we have an antiferromagnet and a pseudogap phase. Those are actually, in a sense, the analogs of the hadron gas in our phase diagram. This is our phase diagram. Temperature on the vertical axis, our version of doping on the horizontal axis. Doping for us is excess of quarks over antiquarks, or excess of baryons over antibaryons. And what you see here is that when you do collisions at very, very high energies, you make so much entropy that you have almost the same number of quarks and antiquarks. The large LHC collisions, you produce matter way, way up here at the top left. This droplet of matter expands, cools downward, cools downward, and then turns into hadrons. You go to lower collision energies, though, at RIC, not quite as high energies. You make a quark gluon plasma with a little bit more quarks than antiquarks because you haven't made quite as much entropy, and you cool down this line. And now what you see is that if you want to explore this phase diagram, you need to go to lower and lower collision energies. And in fact, the relativistic heavy ion collider at Brookhaven has spent the last 3 years doing a program called Beam Energy Scan Phase 2, because as I'll say, several years ago, they did an exploratory version of this, which showed interesting results and motivated the program that has occupied the collider for the past 3 years. And in this energy scan, they are studying heavy ion collisions with this energy, this lower energy, this lower energy, this lower energy, to map out this region of the phase diagram. Why are they doing that? Why are we doing that? Well, it's because what we now know from lattice QCD is that in this yellow region is the region of the phase diagram which is well understood. We have a crossover. The quark gluon plasma and the hadron gas are connected smoothly but continuously, as I showed you in that very first slide. And the question then emerges, how does quark-gluon plasma change as you dope it? As you go to a larger excess of quarks over antiquarks? In this yellow region of the phase diagram, we know the answer quite well from lattice calculations, but those lattice calculations become harder and harder as you go to higher and higher doping. And the big qualitative question is, does this crossover become a first order phase transition? There's a whole variety of model calculations that say that at a critical point, just like the critical point in the water steam phase diagram, this crossover between the original liquid and familiar protons and pions, this crossover becomes a first order transition at a second order critical point. This is only known in model studies. The big open question is, does this happen in nature? In principle, this could be answered theoretically, but for reasons that I won't explain, lattice calculations become exponentially more difficult as you step off towards the right here. And each step to the right in doping makes the lattice calculations difficult by a multiplicative factor. So it's very, very difficult to push to the right with theory alone. But just to give you a sense that the theory is well under control, I'm actually not going to explain this diagram, but this is the confluence of all these bands, the gray bands and the colored bands on these black dots, tells us that the combination of lattice calculations plus experimental measurements, we have a very good idea of what's going on as heavy ion collisions pass each of these red dots. And we have a very good idea of what's going on from the lattice. So everything hangs together in this region. We have a crossover. It's not that different than on the vertical axis. The question is what happens out here, and for that we need experiment. Sorry. So sorry about that. Here we go. So exploring this phase diagram is the goal of this beam energy scan program at RIC. There are beautiful but exploratory results from the first beam energy scan phase 1. Low statistics runs at all those energies. So at all those places in the phase diagram, low statistics runs, maybe only 100,000 events or even a few tens of thousands of events. So just an exploratory study. In that exploratory study, there are, so look at these top two panels as a function of baryon doping. So this is the left side of the phase diagram. You go farther into the phase diagram. Do you do heavy ion collisions at lower and lower energies? For both of these observables, there are interesting and non-monotonic dependencies. I'm actually not going to describe the second one. I'll show you the first one again in a second. These kinds of results from this exploratory study, they all have large error bars because the statistics were so small. But they present an outstanding opportunity. They motivate the current experimental program at RIC. And they present an outstanding opportunity for theory. And outstanding opportunity is another way of saying a really difficult challenge. Because interpreting the data in these lower energy collisions is actually much harder than at the very high energies. You need the hydrodynamic calculations like before. But the hydrodynamic fluid now is doped, and that's an additional degree of difficulty. The initial state lumpiness is very important now because the hydrodynamic fluid doesn't live as long, and that initial state has to be treated in a way appropriate for these low collisions. That's also a new challenge. You need to figure out quantitatively how much of the protons and neutrons, the baryon number and the initial nuclei, actually get stopped in the fluid and how much just fly through. That's also a new challenge calculationally. And then you have to ask, well, those are all just sort of bread and butter challenges. They're big challenges, but they're nothing to do with the critical point. Then you have to ask, how can we look for the critical point? And I'll get to that. So I want to highlight one of the experimental measurements from the first low statistics phase of this program. What the experimentalists did here was to do, let's say, 10,000 collisions, 100,000 collisions at each energy. So each of these red points here is one collision energy. you can see at the lower energies, the statistics were much worse. This is actually less than 10,000 collisions. And what do they measure? Well, they count the number of protons minus the number of antiprotons in each of those collisions. And they make a histogram. And you know from the central limit theorem that if the statistics are if there's nothing interesting going on, you're just going to get a Gaussian distribution. And you now look at deviations from the Gaussianity of this distribution, and the deviation you look at is called the kurtosis. So it's a measure of the shape of that distribution. It measures its tails. So which is to say, it's telling you about fluctuations in the number of protons produced in the collision. And those fluctuations, or the kurtosis of those fluctuations, as you reduce the collision energy, increase the doping, first it goes negative, and then it goes positive. Well, maybe I'm being a little over exuberant. It goes positive, but the statistical significance is really poor. That's the current state of play. And I walked you through that because that is the answer to the question of how can we see a critical point if there is one. If you could really believe that this observable as a function of doping first goes negative and then goes positive, that is a telltale signature of a critical point in the phase diagram, as I'll explain to you. And but you shouldn't believe what I just said from the data, because look how big these error bars are. Are you really sure that this is negative? Well, 3 negative points. Maybe this negative trend is robust, but certainly you should not believe me that it has turned positive, because these two are consistent with 1, and this one has huge error bars. But a negative contribution to the proton kurtosis could be a harbinger of the approach to a critical point. The signs of this upturn are encouraging, but we need higher statistics. On the experimental side, this has been the purpose of the 3 years of running at RIC, which will come to a conclusion this June or July. So this experimental program concludes this June or July. We will have high statistics, much higher statistics, at least 1 million events at every energy will be recorded by the end of this July. Probably about a year from July, we'll start to hear results. So great, we're going to know the answer. But you'd like to be able to draw a theory curve that goes that is quantitative prediction of this observable, and that's the challenge that I and many others are working on right now. Once you've dealt with those earlier challenges that I described for how to interpret data at these low energies, you then have to add hydrodynamic fluctuations and the fluctuations that are characteristic of a critical point. Critical point in a phase diagram is a place where fluctuations are enhanced. You need a self-consistent treatment of the fluctuations, describing how they evolve in an expanding cooling droplet of plasma. And that is one of the central goals of the beam energy scan theory collaboration. We are a group of theoretical physicists formed this collaborative of, there were 12 different universities, and maybe one of our cleverest things that we've done was to invent this acronym. We are the Beam Energy Scan Theory Collaboration, which means everyone calls us the best collaboration. That's really where we are. But I'll say a little bit more. Why do I expect negative and then positive for that result? It's because I know, although I don't know whether we have a critical point, I know a lot about what will happen if we have a critical point. And the reason has to do with what's called universality. This critical point is in the same universality class as the Ising model, sometimes mispronounced the Ising model, of condensed matter physics, of statistical physics. And an enormous amount is known about the critical fluctuations that happen near this critical point. And in fact, in a region shown here in blue, the kurtosis of those fluctuations should be positive. In a region shown here in red, the kurtosis of those fluctuations should be negative. These kinds of things we know reliably if there is a critical point. And you can see that with this shape, as you do heavy ion collisions at lower energies, lower energies, lower energies, first you should see a negative kurtosis, lower energies, lower energies, lower energies, then you should see a positive kurtosis. And in fact, the magnitude of the positive region is higher than the magnitude of the negativeness of the negative region. So you should see a small negative excursion and then a large positive excursion. And that might be what we're seeing. The data taking will be completed in 2022. The hints that we have from the exploratory data will become reliable experimental measurements. We don't know yet what they will tell us, but the error bars will be much smaller. And just one slide to give you references to my current work. What I and collaborators are right now developing is a self-consistent treatment of critical fluctuations, which are out of equilibrium in an expanding cooling droplet of this hydrodynamic fluid. And there's a complex interplay between the expansion and cooling dynamics of the bulk fluid and the fluctuations themselves. That cooling drives the critical fluctuations out of equilibrium. The out of equilibrium critical fluctuations modify the expansion itself. So there's an interplay. And then furthermore, the expanding fluid carries the fluctuations with it. So even if the critical region is here, the fluctuations get carried outwards. All of that we now have a way of modeling self-consistently. The last step in this modeling before we hand this new set of tools over to the people who, in the best collaboration, who do the large-scale simulations, the last step is to freeze out. We need to turn these fluctuations into the kurtosis of the proton multiplicity distribution, which is what the experimentalists measure. And that is my current work in progress with Manisha Pradeep, Misha Stefanov, and Yi Yin. Okay. How much time do I have? 15 minutes, Alok, is that right?
In fact, you could go up to even 20. That's okay.
Okay. So in the last part of my talk, I'll come to the second completely different what's next question. Okay. So we've learned that these collisions produce this strongly coupled fluid. We've learned that the original liquid is a liquid, it's not a gas. I've talked with you about how we are right in the middle of an experimental and theoretical effort to understand its phase diagram. Now, let's go back to the highest temperatures we achieve. So go back to Large Hadron Collider collisions at the very high energies. Forget doping. We're not. We talked about that in the previous part of the talk. Let's go to the undoped quark-gluon plasma produced at the very highest energies, and ask, my goodness, this liquid is 5 trillion degrees hot. How can it possibly be a liquid at 5 trillion degrees? And this is a question of saying, well, what I'd like to do is study this liquid microscopically and see how it's put together. I'd like to understand how this strongly coupled liquid emerges from the fundamental theory of QCD, which I know, if I look at it microscopically, is weakly coupled. This is the question that you'd like to answer by probing the internal structure, the microscopic structure of this liquid. And the question, again in red, is how does the strongly coupled liquid emerge from an asymptotically free gauge theory? This word emerge is a wonderfully slippery word. And in fact, the word emerge can have 3 different meanings. And if I had another hour, I would talk about all 3. Here's 3 different meanings, and I'm going to, in fact, only speak about the first. So one use of the word emerge, and it's the most common use of it in condensed matter physics, is to say, if I vary the resolution of my microscope, so if I look at this liquid with a very high resolution, so I'm looking at it on very short length scales with a very precise microscope that allows me to see its structure on very, very short distance scales, then I will know I must see weakly coupled quarks and gluons, because QCD is weakly coupled at short distances. Now let me coarsen the resolution of my microscope. As I look at it on longer and longer and longer length scales, by the time I get to a length scale of 1 over the temperature, I see a liquid. So how does the liquid emerge as I make my microscope coarser and coarser and coarser, as I make my resolution scale coarser and coarser and coarser? That's one meaning of emerge. Another meaning is emerge as a function of time. And this is a lot of work has been done on this in the last 5 years, but I won't have time, pun intended, I won't have time to talk about it today. But how does this strongly coupled liquid form? You do a collision. At time zero of the collision, you don't have a liquid, you have a collision. How does the liquid emerge as time progresses? We know that it does, but what are the dynamics of the formation of this liquid? Very interesting question, which I won't have time for today. And then the last one is, which also I have one slide on, but I'm going to skip, is you can look at droplets of the liquid of different size. And we know for a droplet the size of a lead nucleus, so you collide 2 lead nuclei, make liquid. What about colliding 2 protons? Does that make a liquid? What about colliding 2 carbon nuclei? Does that make a liquid? What about colliding 2 copper nuclei? Does that make a liquid? What's the smallest possible droplet of this liquid that behaves like a liquid? This is another great question. All 3 of these questions are questions on which there's been enormous effort in the past 5 years. On the first and the third, that effort has included experiment and theory. This second question is really, in its essence, a theoretical question, which actually I'm going to come to in an indirect way. I will skip my slide on what the smallest possible droplet of liquid is because it's not the main direction I want to go. So I'd like to probe the structure of this liquid on different length scales. How can I do that? To see the inner workings of QGP, to see how it's put together from quarks and gluons, I'm going to need probes with very high resolution. I need a resolution scale that's much smaller than the size of the proton. I need to look at the structure of this liquid on length scale smaller than the size of a proton, so that I can see its structure on length scale smaller than 1 over its temperature. For the experts in the room, you immediately think of 2 possible probes, upsilons and jets. Upsilons are not a good choice, but I'm not going to take the time to explain that to all of you. Jets are the best answer we have, so I'm going to skip to jets. What is a jet? Well, when I collide 2 nuclei, somewhere in that collision, I might have a hard scattering of a gluon with a gluon, or a quark with a quark, or a quark with a gluon that creates, let's say, 2 quarks come in, 2 quarks get scattered at a large angle, and I get these 2 high energy quarks going off at large angles. But remember, they're in the soup. So I've got these 2 quarks shooting off at very high energies, and they're going to shoot through the soup. If this was 2 electrons, then all of a sudden I've got myself the possibility of doing electron microscopy of the quark-gluon plasma, because I would have an electron shooting through the quark-gluon plasma, and I could use that as a probe. Unfortunately, it's not 2 electrons, it's 2 quarks. Quarks don't stay quarks. They form into showers of particles called jets. So what I get is 2 jets shooting through the plasma. And these jets are now probes of the plasma. And these are the best, in fact, really only chance we have of seeing the inner workings of the quark-gluon plasma. What would be wonderful, but is impossible, is to say, okay, to my friends, the experimentalists in Geneva, please make me a drop of this liquid. And they say, sure, we just did it in a collision. Okay, now bring that drop of liquid across the Atlantic Ocean and take it to Stanford and put that drop of liquid in the Stanford accelerator, so that Stanford linear accelerator. That will shoot a beam of electrons at it, and we'll study its structure. That's how we learn the structure of the proton, after all. So let's please bring a droplet of your liquid from Geneva to Stanford, shoot a beam of electrons at it, and we'll learn its structure. The catch is that the droplet of liquid they make in Geneva only lives 10 to the minus 21 seconds. There's no time to take it to Stanford. So you can't ever take a drop of this liquid, bring it to an electron accelerator, and study it the way you study materials at SLAC now, or the way we studied the proton at SLAC in previous years. So our best chance is to look at these jets, which it's as if you have a little electron accelerator inside the same collision in which you made the liquid, except it's not an electron accelerator, it's a jet. And so these jets are the closest we will ever come to doing a scattering experiment off a droplet of Big Bang matter. It's not as good as a controlled scattering experiment, but it's the closest we'll ever come. Right. So to restate the question, I want to use these experiments to answer the question of what is the microscopic structure of this liquid. And the long-term goal of this experimental program, maybe sometime in the middle or second half of this decade, is to use these jets as if they were a high-resolution microscope trained upon a droplet of QGP, and to use these jets to look for, like to do deep inelastic scattering off the QGP, to look for large angle scatterings. I have a particle in the jet, it's flying through the soup, it scatters at a large angle, and that tells me that it scattered off a point-like particle in the soup. That's a way of resolving point-like particles in the soup. And that is the long-term goal. Jets do not make this easy. Jets are not an electron accelerator. In ways that I will try to give you a sense, this program I've just described in a cartoon form is actually very challenging, and it needs very high statistics data. So much so that at Brookhaven, a brand new detector is being built right now. It will take first data in 2023. It's called S-Phoenix. Its purpose is to study jets in heavy ion collisions at RIC. Thankfully, at the LHC, we don't need a new detector. We have CMS and Atlas, which are the world's greatest jet detectors. S-Phoenix is like a little mini CMS or a little mini Atlas being built at RIC, and will start in 2023. The same year, 2023, will also be the beginning of the high luminosity program at the Large Hadron Collider, when much higher statistics jet data will start to come from the LHC also. So really, 2023 is the beginning of the high statistics jets data sets at both sides of the Atlantic Ocean. So we're here in 2021 right now. We don't have the high statistics data yet. What we can do, though, is to use the data of today to build the baseline of understanding, to understand the whole set of complex phenomena, the small corrections to which will be what's of interest in the mid or late 2020s. There are various theoretical frameworks for doing this. I'm going to mention the lessons we've learned in one particular model framework called the hybrid model, but I'll try to focus on general lessons. So what is the hybrid model? This is the fourth time, I think, if I'm counting right, that these cousins of QCD are going to come in a certain specific and limited way. So what we observed, this group of people listed here, but we observed going back to 2014 for our first paper in this direction, is that really to describe jets in heavy ion collisions, you need a sort of a mixed up description, because jets are fundamentally perturbative. The production of that very high energy quark is a perturbative QCD production process. The fragmenting of that quark into a shower is a perturbative weakly coupled phenomenon, well described in ordinary perturbative QCD. But the soup is a soup. The medium is a strongly coupled liquid. So now I've got a perturbative object plowing through a fundamentally non-perturbative medium. And furthermore, the energy that, so this jet loses energy to the fluid, and the energy that the jet loses very rapidly becomes one with the medium. It turns into flowing medium. It creates a wake. So we need a hybrid approach. And that's the basis of the model that I'm talking about. But it is a model. It's not a rigorous calculation. We think of each parton in a parton shower with a conventional QCD tool called Pythia. So I have this shower of particles. Every particle in the shower loses energy into the soup. It has a dEdx, energy loss per unit distance traveled. And we're going to take that dEdx from a calculation done in this cousin of QCD. This is how that calculation works. How am I doing on time? I'm not sure that I should take the time to walk you through this, but the essence of this new method of calculation that comes to us from string theory is to describe a gauge theory phenomenon in an analog or dual description that is in one higher dimension. So there are two dimensions shown on the slide. Left to right, this is the direction of propagation of the quark. The end of this red line represents the quark. So the quark starts here, then it's here, then it's here, then it's here. The quark is moving left to right. This vertical direction is the fifth direction of this holographic description. And it represents actually it represents scale in the gauge theory, not direction, but scale. And so the fact that this quark is at the end of a red line, these red lines are actually strings from string theory. And as this quark travels, it has to stretch the string. That stretching the string saps energy from the quark slows down, and ultimately this quark falls down and falls down and falls down into this. What's this horizontal line at the bottom of the diagram? It's actually a black hole horizon. So in this dual description for the QCD plasma, or the cousin of QCD plasma, the temperature is, the fact that this is a hot system is represented by the fact that there's a black hole horizon down here, which has a Hawking temperature T. And so when you create this high energy quark, it shoots off, it shoots off, it shoots off, and it falls into the horizon. That in our world is you shoot this quark through the plasma, it loses energy, and then it thermalizes, it stops, it becomes part of the soup. And there's a simple formula. It's an analytic calculation. This formula is not known in QCD, but in this cousin of QCD, it's known. Here's the EDX. It's a simple formula for how the energy loss occurs as a function of the thermalization distance. And the thermalization distance itself depends on the incident energy and the temperature in this funny way. And we put one free parameter into our model, recognizing that the calculation is in a cousin of QCD and we care about QCD itself. We introduced this one free parameter called kappa here. Kappa is known to be between 1 and 1.5 in the cousin of QCD, and we'll see what it turns out to be in QCD itself by fitting to experiment. So we build this model. It's like a centaur. It has a QCD head and a holographic body, or vice versa. We're putting together perturbative description of the jet and non-perturbative description of energy loss taken from this calculation done in a cousin of QCD. And then we start describing data. And I'm going to give you the gestalt of this without walking you through the definition of every observable. There's one free parameter, I have to fit it. So here's one experimental data point. I use this one experimental data point to fit the one parameter in the model. And then I compare the predictions of this model to every other data point on all the slides I'm about to show you. So this is a fit. The fact that, and the experimental predictions here are the pink bands. But then the fact that the pink bands describe all these data points well, that's in fact a success of the model. Here's 5 observables. The black points are the data, the pink bands are the model. I fitted the one parameter of the model once, and I described all these data points. That was data that we had already in 2014. We then in 2014, actually in 2015, made a set of predictions before the experiments were made. In 2016, a whole new set of experimental data was released. The data is in black. These are plots from the experimentalists at the conference at which they showed this data for the first time. Our theory curves, you can see other people's theory curves in other colors, but ours are green here. So look at green theory compared to black data points. Look at green theory compared to black data points. Look at green theory compared to black data points. Look at green theory compared to black data points. One more, one more, one more. And so that was 2016. And so we made this initially crazy sounding model where we combined QCD and a cousin of QCD in the way I described. We described jets with a traditional QCD approach, but then we described their energy loss in the way that I described in a quite non-traditional way. And that description, after fitting one parameter in the model, and the fit value, by the way, translates into the stopping or thermalization distance in QCD being about 3 or 4 times longer than the stopping or thermalization description in the cousin of QCD, which is quite a reasonable result, in fact. It describes a whole host of data. All of those observables, though, were chosen to be observables that are sensitive to energy loss. So I think at this point, we actually have a pretty good understanding of how, when I shoot this jet through the plasma, how the partons in the jet lose energy. But that doesn't get us anywhere closer to looking for those large angle kicks. A large angle kick changes the shape of jets. So we have to start talking about the shape of jets, not just how they lose energy. And how is their shape going to be changed? So your first expectation is that the way the shape of a jet is changed is that all the partons in this jet shower are going to get kicked, and the jet is going to get fatter because the partons are all being kicked as they go through the medium, and the jet must get fatter. Those kicks will be Gaussian distributed in a liquid. And if you think about this by analogy to Rutherford scattering, this was Rutherford's original expectation. It's not what Rutherford saw. Rutherford expected that atoms were soup or jelly. When he shot his alpha particles at the atoms, he expected they would pick up a small amount of their direction would be changed a little bit, just a Gaussian distribution of kicks, small kicks, because you're going through a liquid. So here we have a liquid, I have a jet going through it, pick up small kicks, the jet should get fatter. That's the analog of what Rutherford expected before he made his famous discovery. And what we are expecting is the analog of Rutherford's actual discovery, which is that once in a while, a parton will get a large angle kick because it will see the point-like substructure of this liquid. So to see the inner workings of QGP, we need to start by finding this Gaussian distribution of soft kicks and then look for the rare large angle scatterings. So it doesn't sound too bad, but I've left out 2 very important, much larger confounding effects, which I'll try to give you a sense of, but I'm out of time, so I will cut to the chase in a minute. So the first confounding effect is that when you actually start looking at data, you see that jets are narrower in heavy ion collisions, not wider. Why on earth is that? I just told you they're picking up kicks, they should get fatter because all the partons are getting kicked, they should spread out. The reason for this is it's actually parton energy loss. So when you observe a jet in a heavy ion collision, what does that mean? It means you say, well, let me count and study the number of jets with an energy bigger than 50 GeV. Those jets that you select in that way will be the jets that have lost the least amount of energy. Because a jet that lost more energy won't have 50 GeV anymore. But then you could say, well, okay, well, wait. The 50 GeV jet, that could be a 100 GeV jet that lost an enormous amount of energy. But then I say, oh no, there are orders of magnitude fewer 100 GeV jets in QCD than there are 50 GeV jets. The jet production is a very steeply falling function of jet energy. So when you look at jets in a heavy ion collision and you say, let me count the jets and study them, the jets with energy bigger than 50 GeV or energy bigger than 60, any cut like that, that introduces a selection bias. You select the jets that have lost the least energy, and it turns out that those are the narrow jets. One of the things we've learned in the last few years from a whole variety of directions is that wider jets lose more energy than narrower jets. So if you select jets that lose least energy, that will give you the narrow jets. So even though if you could follow one jet in a heavy ion collision and watch like a movie what's happening, that one jet is getting wider as it loses energy. Because of this selection bias, you select the jets that have lost the least energy. That means your sample of jets will be narrower in heavy ion collisions than in PP. So this is a this is a plague upon those of us who study jets and heavy ion collisions. The other confounding effect is that there's another effect that makes jets wider. Not just the kicks that we're looking for, but also when a jet goes through the soup, it leaves behind a wake in the fluid. The jet loses momentum. That means it has to dump momentum into the fluid. So the jet goes through, and what's left behind is moving fluid. But when moving fluid turns to particles, that will turn into soft particles, PT of 1 GeV, 2 GeV, going in the direction of the jet because it was moving fluid. And the part of the talk that I will have to skip is experimental data that shows we can see that moving fluid. We were learning a lot about it. And I just need to skip this because I want to come to my punchline. I will just say that our characterization of the wake of that fluid, that's something that I and others are working on right now. It's on a good track. It's not yet perfect. This group of us, this is Casaldere Solana, Miliano, Pablos, me, and Yin, are improving the description of this wake right now. You have to get that right if you want to look for the soft kicks. You have to get the soft kicks right if you want to look for the hard scatterings. That's the program that we're in the middle of. I said here the goal for the 2020s. I think it's the goal for the late 2020s is to look for the rare large angle scatterings. Just to give you a sense of how rare they are, this is a toy model calculation from 2018. I will show you, yeah, let's use this one. So this is an incoming quark going into a brick of quark-gluon plasma, a brick with length L. So it's not a full model of a heavy ion collision yet. And you ask, what's the probability that you see a particle with momentum p scattered by angle theta? And if I take the momentum, the temperature to be 400 MeV, the incoming momentum to be 40 GeV, and let's look at this middle red line here. That's a scattered particle with momentum bigger than 8 GeV. So 40 GeV particle comes in. What's the probability that I see an 8 GeV particle kicked out with an angle theta of 0.8 radians? Well, it's about 10 to the minus 2. So a 40 GeV parton in the jet kicks a 16 GeV parton out to a theta of bigger than 0.4 radians, or an 8 GeV parton out to a theta bigger than 0.8 radians. It's a probability of 10 to the minus 3. Let me just check that. Yeah, you have to integrate this curve, and you get a probability of 10 to the minus 3. So in 1 in 1,000 events, if this little toy calculation is indicative, in 1 in 1,000 events, a 40 GeV parton in the jet will scatter an 8 GeV parton out at an angle of 10 to the minus, at an angle of bigger than 0.8 radians. That's possible to see if you have statistics with millions of jets, which we will have in the mid and late 2020s. It's not easy, it needs this high statistics, and it needs good systematic control of every one of these confounding effects that we're right now busy understanding. So that's a sense of where we are. I should say that this effect of this wake, which I described to you as an annoyance, it's a confounding effect. It's actually very, very interesting in and of itself, because it gives us a way of studying how quark-gluon plasma forms and equilibrates, because you sort of shock the plasma with this jet going through it, and then you can actually study the wake and look to see how it re-equilibrates and how fast it equilibrates. This is actually our first experimental handle on equilibration in heavy ion collisions. So where are we now? We're learning more and more now, and in the short term and in the medium term. Parton energy loss, I think we understand well now. How the medium responds, namely that wake, we're getting a better understanding of that. We need to study more sophisticated observables. We're actually working on that also. I haven't described it today. All of this is setting us up to use jets as precise, controlled, as close to controlled as possible probes of the inner structure of the quark-gluon plasma. All of this today's sort of illustrative calculations, there's a lot of hard work ahead defining, calculating, and then measuring these observables that will allow us to look for events in which a 20 or 40 GeV parton scatters off a quasi-particle that must be there if you can resolve the microscopic short distance structure of the soup. And that's the goal in this second what's next question. So taking the long view, I've told you about two what's next questions. One is doping the quark-gluon plasma, mapping the phase diagram, perhaps finding a critical point. The experimental data there, the data taking finishes this July, results from the experiments maybe a year from July, and we theorists have to be ready. Ongoing right now is understanding the wake in the plasma. By detailed comparison between a baseline, which assumes a hydrodynamized wake, and the data, we can learn to what degree this wake does and does not thermalize and get experimental access to the equilibration question. How does quark-gluon plasma form as a function of time? And then in the mid-2020s, the longer-term motivation for jet studies in this field is to use high statistics jet data that our experimental colleagues will be taking starting in 2023 at both RIC and the LHC to look for these large angle scatterings that will give us access to the microscopy of quark-gluon plasma. And there I will end. Thank you very much.
Thank you so much, Professor Rajagopal, for that incredible lecture and the tour through QGP and heavy ion collisions. Thank you so much. Can we have a round of applause for Professor Rajagopal's beautiful lecture?
Okay, I see that there are questions in the chat. Do you want me to look at them myself, or are you going to pick them out for me?
I think let me do the needful, and I'll just put them up to you.
I muted for a second. Can you hear me now? Alok, can you hear me? Alok, you're muted now.
Oh, shoot.
There you are. Can you hear me?
Okay. So, yes, and I hope you can hear me as well.
Yeah.
Okay, very good. So there are a couple of questions on.
So I'll start at the bottom. Suraj wants to know: is this going to be on the test? Do I get to give you a test? Do I get to give you a test?
I don't know.
I'll have to think about test questions, Suraj. You've set me a challenge. Soman says, what are the questions that S-Phoenix will address that were not covered by jet studies in the LHC? That is an excellent question. First of all, both S-Phoenix and the LHC of the coming years will have much higher statistics than the LHC of the past few years. That's one answer, but that doesn't answer your question. The answer to the question is that S-Phoenix, I don't want to say advantages, it will have two potential advantages, two significant differences. One is that the plasma is not quite as hot at RIC than at the LHC. And so, that means that the temperature is not as high. 1/, the temperature is a little bit longer length scale. And if I want to probe the plasma on length scales that are shorter than 1/, temperature, that's an easier challenge at RIC than at the LHC, because 1/, temperature, T is lower, 1/, T is longer. So the microscope I need at RIC, I don't need as powerful a microscope at RIC as at the LHC. That's one reason. The other reason is that jet studies at the LHC, it's hard to look at sort of 30 and 40 GeV jets at the LHC because they're swamped by background. Whereas at RIC, it'll be possible to look at 30 and 40 GeV jets very easily, even 20 GeV jets very easily at RIC. Backgrounds are less, backgrounds for jet studies. And that means that if it's a question of where you think the interesting physics will lie. If the interesting physics will be seen by looking at 300 GeV jets, go to the LHC. If the questions will be addressed by you looking at 30 GeV jets, go to Rick. And I don't think we know the answer yet. But basically, by comparing measurements at Rick and the LHC, you have control of two systematic effects. One is the temperature of the plasma is different, and the other is the energy of the jets are different. You shouldn't take theorists too seriously on a question like this. We'll see what the experiments yield. But my theoretical prejudice is that it will be easier to see the microscopic structure of the QGP at slightly lower temperatures and with lower energy jets, which favors Rick. But then again, remember that theorists were expecting a gas and we got a liquid. So it's I think the best answer is that you want to be able to compare results at Rick and the LHC, and we'll learn the most via having both and comparing the results. Okay, so I'm going upwards on the chat here. Is there any time dependence of the quantum fluctuations? Very Lorentz contraction at different spatial positions in the fluid. Yes to both. So this is Deepan's question. Is there any time dependence of the quantum fluctuations? There, what happens is that the initial quantum fluctuations equilibrate as a function of time and get washed away. So there's a time dependence of the fluctuations. I'm not sure if this is what you meant, but the quantum fluctuations the initial quantum fluctuations as they equilibrate get washed away. And that's a time dependence. The other time dependence, if you have a critical point, is that as the expanding cooling droplet passes the critical point, the critical fluctuations grow with time. That's the other time dependence. Varied Lorentz contraction at different spatial positions of the fluid, that is likely a small effect, but in principle, the answer is yes. Could I elaborate on strange metal and quark gluon plasma? Yeah, that's slightly metaphorical, but the strange metal phase, like the quark gluon plasma phase, is one in which the correlations in the strange metal phase, the correlations between the electrons are so strong that there's no quasi-particle description of the strange metal phase, and that's why it's called strange. And that's really the analogy. The other analogy is that in that phase diagram, it's the high temperature phase. So they're microscopically very different. The theories are very different, but given where it sits in the phase diagram and given that it is, it's the strongly coupled fluid phase of the theory. It's the phase of the theory in which there's been no symmetry breaking yet because of the high temperatures. In that way, it's similar. Okay, and the last, although it's the first because I'm going upwards in the chat, strange metals, I think I just did, antibaryons. In the standard model of particle physics, we have electrons and anti-electrons. They're called positrons. We have quarks and anti-quarks. From 3 quarks, I can make a proton. From 3 anti-quarks, I can make an anti-proton. And if a proton and an anti-proton ever meet, they annihilate and turn into quarks, gluons, photons. I'll let you learn more about that on your own, unless you have further questions. Okay, so Soman, thank you. Okay, so now I can take other questions. Alok, if you want to take other questions, I think I've done the ones from the chat.
I think those were the ones. Maybe I could squeeze in a little tiny question of mine.
Sure.
Being a string theorist, I'm curious to know about the fact that the hybrid model that you talked about, there was this parameter called kappa in dE over dx.
Yes.
What would that correspond to the on the holographics and the gravitational dual side?
It's a function of the 't Hooft coupling, when you put in reasonable values. So speaking to you, since I know you know what the 't Hooft coupling is. When you put in reasonable values of the 't Hooft coupling, its kappa is between 1 and 1.5. I've actually forgotten right now what the expression for kappa is in terms of the 't Hooft coupling, but I could have written if we were interested in the holographic theory itself, and I would never have introduced kappa. I would have written it in terms of the 't Hooft coupling. But we decided to replace that by a free parameter and fit that free parameter to data. That was our way of allowing for the possibility of differences between QCD and n equals 4 superyoung
Okay. All right.
Anyway, if you ask me by email, I'll point you to it in the literature.
Okay. And just one last quick question, though you did not cover it in your talk, but I'm very curious now that we have you here. So what is the status of the study of color superconductivity holographic?
Oh, great. I should have made it mention. Yeah. So let me share screen a minute, because this one I'll answer not just for you, but for everybody. That previous answer was really just for Alok. Let me share screen. Share. And let me go all the way back to one of my phase diagrams. By the way, I'm happy to give you the slides, Alok, if you would like.
We would appreciate that a lot. Yes, we'll put it up on the website. Yeah.
Yeah, great. So
Thank you.
if you look at this phase diagram, which I showed multiple times in the second part of my talk, this high density, low temperature phase of matter is what Alok was just asking about. This is a color superconductor. So what is this? Nuclei live here on the phase diagram. Take two nuclei, take nuclear matter and squeeze it, but without heating it. So I need some way of taking nuclei. I'd like to make them big, please. The bigger, the better. And I'd like to squeeze them, but not by heating them up. So no heavy ion collisions, that's no good. That makes high temperature. So I've just described a neutron star. Neutron stars are giant nuclei. They're the size of they're nuclei that are 10 kilometers across. They have the mass of the sun in a volume of a sphere of 10 kilometers radius, roughly speaking. So they're like giant nuclei. And at their center, they have densities that are denser than the density of nuclei. So the only way we know of starting here at nuclear matter and going to the right is to look inside neutron stars. Well, what do we know theoretically? We know that if you go into this region of the phase diagram where you've crushed the nuclei to such high densities that protons and neutrons no longer exist, then I have cold, dense quark matter. And that's like a Fermi liquid. It's for quarks or fermions. And anytime in any Fermi liquid, if the quarks attract each other, they form Cooper pairs at low temperatures and you get a superconductor. And that is indeed what happens with this Fermi liquid. The quarks pair and these Cooper pairs make it a color superconductor. And back in the period, let's say between, well, my first paper on this was 1997. Back in the late 90s and the first half of the 2000s, many people, me included, but a large community of people worked out the properties of color superconductivity from first principles far to the right at very high densities where all the calculations are well understood. And we made our best effort to predict the properties of the matter down here, which might be achieved in neutron stars. And then I see Rishi Sharma entering. Rishi, if that was you, you should say so. So I have a former student named Rishi Sharma. I don't know whether the Rishi Sharma who just entered the waiting room is my former student, Rishi Sharma. If so, Rishi is one of those who's a world expert on this form of matter. He's now a faculty member at TIFR in Mumbai. Anyway, Rishi, if that's you, you should say so in the chat. And what's really potentially very exciting now is that, why did I stop working on this in around the period of 2005 or so? One reason is that heavy ion collisions got interesting, at least from my perspective, and I continue to think that. The other reason is that I realized that it was very hard to get an experimental handle on the properties of matter in the middle of a neutron star. Neutron stars are, megaparsecs, or well, far away. They're spread out around our galaxy or in other galaxies. And if you see photons coming from a neutron star, they come from the surface of the neutron star. So the great news is LIGO and Virgo. And in fact, I know that LIGO India is under construction that will add to the experimental results in this domain. So LIGO studies the gravitational waves when two neutron stars spiral in on each other and merge. And from those gravitational waves, you can learn about the entire structure of the neutron star. And in principle, you can learn about its density profile in the density profile of the middle. And there's now, I would say, circumstantial evidence that there may actually be quark matter in the centers of the heaviest neutron stars. So I would say we're on the edge of starting to learn about the properties of matter here from astrophysics of gravitational waves coming from neutron stars. I am no expert on the calculations associated with those astrophysical properties. I have colleagues at MIT who are. So I'm paying a lot of attention to this, but I'm not doing the calculations that are necessary right now. The reason I'm paying attention is that as we start to have a library of such events, we may start to learn about the properties of matter just here which I'm circling with the cursor, which would be a tremendous development. For the last few minutes, I've been speaking wearing my optimistic glasses. We'll have to see what happens.
All right, thank you. Thanks so much. I think with that, we come to the
I'm just curious. So I saw there was a Rishi Sharma who just entered from the waiting room. Rishi, if you're my former student, please say so in the chat. If not, someone should say hi to Rishi from me. But anyway, nothing in the chat. So maybe it's somebody else. It's not an uncommon name.
Yes.
Oh, it is
okay, I can't unmute. So let me unmute.
Anyway.
Hi, Krishna.
Hi, Rishi. It is you. Well, great to see you. You missed the talk, but anyway.
I had something, but yeah, I was hoping to join.
Yeah,
nice to see you.
Great to see you. So Rishi, let me introduce you to Alok's audience here.
Hi.
If you have more questions about color superconductivity, Rishi, you can ask Rishi as well as me. But thank you very much for the invitation, Alok. I have something at 10, we're just at 10, so my phone may ring. But it's been a real pleasure, and
Thank you.
It's great that you're doing this.
Thank you.
It seems like a great colloquium series, and my best wishes to everyone.
Thanks a lot. Thank you. Thank you so much. So I guess
Rishi, we should talk soon.
Yeah, great. So so I guess on that note, we would end the talk today. Thank you so much, Professor Rajagopal. Thank you so much for agreeing to give this talk. It's a beautiful lecture. Thanks once again. And thanks everybody in the team. So we have this beautiful team of the Physics and Astronomy Club. I call them the Packers. And also the Roorkee Chapter of the Indian Physics Association, pitching in, giving us the tech support. Thanks once again. And bye-bye. Please stay safe.
Yeah, stay safe, everyone. Thank you very much.
Bye-bye. Thank you. All right, team. So I'm ending the meeting. Thanks once again. See you this Saturday.